Morgan Stanley says, this is their computer team. They did a sort of a multidisciplinary report. They said, in order to keep the world economy growing, we must have quantum computing to solve the problems that we're talking about, and also because of the energy consumption. This is actually something like quantum computing must happen in order to keep the world economy growing, and it's going to be a very large market. Morgan Stanley also posed the question in their title, is this the next computing revolution, or is it just weird science? Right now at D-Wave, we're out of the weird science phase. You can show you things that companies like Volkswagen are doing today with our systems. They're solving real problems. They're solving, like optimizing the flow of real-time traffic data in taxicabs in Beijing. They're working now on doing a materials simulation with our system so they can actually simulate batteries for electric cars so they won't have to build prototypes. And I'll show you more. There are about 80 applications that our customers have already developed for our quantum systems. Now, we actually refer to these as pre-commercial applications. They're real problems. They're not yet quite large enough to actually be in commercial application, but every one of these are real problems solved by people like NASA, Google, Los Alamos National Laboratory, Volkswagen, Airbus, Nomura Security, Standard Chartered Bank, and the list goes on. The things our machine does best are optimization problems and machine learning problems. So about half of these applications are in areas that are optimization, another quarter or so are machine learning. You can see some of the specific examples here. And then quantum simulation and materials properties, and we have a sort of a basket we call cybersecurity, where, for example, some researchers at Los Alamos used our system to study the formation of terrorist networks based on cell phone traffic. You know, very interesting applications being done. And again, there are about 80 of these that are published either in academic papers or in presentations given at our user groups that you can actually look up on the internet. BCG says this will be about a $50 billion market in only 12 years. Nobody really knows, of course. These are not meant to be precise numbers. The point is, this will be a very large market as it develops, because not only will we solve some problems cheaper, faster, better than classical computers, but we will start solving problems that simply can't be solved today because of the complexity of the problems and the limitations of classical computers. Notice also from an investment point of view, the quote at the bottom of the page. This is going to be different than classical hardware. Classical hardware very quickly became commoditized. This is not the kind of hardware that will become commoditized. So we see value creation all through the chain. We're building the hardware and the software, and we'll be working with customers on applications. There will be tremendous value creation throughout that entire chain. In the scientific world, we've recently just published 2 papers. These were papers published in Science and Nature, the 2 leading journals in the world, by D-Wave scientists. This is internal work done at D-Wave. It takes a long time to try to explain what this is, but let's just look at a couple of quotes. Ned Allen, the chief scientist at Lockheed, said, this is the most important work ever done on a quantum computer. It's a premier goal of scientific computing, and it's immediately useful to the technology sector. This is what he said about the work paper published in Science. The guy who won the Nobel Prize Physics in 2016 for the theory behind the other paper said, doing these calculations is essentially impossible any other way. So from a scientific point of view, we're now showing that we can do things that other classical computers can't do, and that quantum computers, other quantum computers, can't even come close to doing. Let's look for a second at the landscape of quantum computing. Now, this is a third-party evaluation. You don't have to believe me. This is Jülich, the National Superconducting Lab in Germany. This is the equivalent of Los Alamos or Oak Ridge National Lab in the US. It's the major German laboratory. They've been studying quantum computers, and they developed a technology readiness level. So it's 1 to 9. If you're at 1, you're Richard Feynman. You just invented quantum computers. It's all theory. It's all a paper. If you're at 9, you're outperforming every classical computer ever built, or even every classical computer that in theory could ever be built. So how are they ranking the industry here? There are some experimental devices at about level 3 and 4. There are various labs and startups around the world and some large companies building small-scale devices that are ranked at 3 and 4. Now there's some other large companies like IBM and Google. Microsoft would probably be down at the level 2 or 3 here, but they published this ranking. IBM, Google, a company called Rigetti, which is probably the leading startup in the field, are at level 5. Where's D-Wave? Level 8. This is how far ahead we are of the rest of the industry. And again, this is not our opinion. This is the Jülich National Lab. We agree with this ranking. You know, we're not quite at level 9. What I'll show you soon is that we're starting to see glimpses of level 9. You know, we're almost there, and as we keep making our system more powerful, we expect that we will be at level 9 very soon, which means we will be outperforming all the classical computers in the world on real commercial problems. To give you a sense of how the industry is developing, here's a history of scaling in the quantum computing industry. There are 2 basic approaches to building quantum computing, quantum computer. One was adopted by D-Wave, that's the blue line, and I'll get to this in a second. It's called quantum annealing. It's an analog device. I'll try to explain it briefly in a second. The other approach followed by everybody else in the field is called a gate model computer. Here's the history of scaling. In the last 15 years, we've gone from 0 qubits to 2,000, and at the end of 2019, we expect to be at 4,000. We'll roughly double the number of qubits every 2 years or so. Keep in mind that straight line means exponential growth because it's a log scale. So we're on a Moore's law progression here with our qubits. The entire gate model community in that time has gone from about 9 qubits to about 20 that really work. Google said 72, nobody really knows if they work or not, so that's in brackets. At any rate, the point here is scaling in these 2 different approaches is quite different. There's an argument about whose qubits are better. If you Google quantum computing, you'll start to see quotes like D-Wave's qubits are better or worse than gate model. All I'll say there is it takes about a full day and 5 years of graduate school to actually follow that technical debate, but now we're actually able to look at real performance. So we're going to just look at what problems we can solve compared to a gate model computer. Rigetti has now published results. We didn't have access to this before because there's almost nothing published on real problems solved with gate model computers, but there is at least this study. Rigetti has a 19-qubit gate model device. They published a paper that said we solved this problem. So our scientists took this problem and they said, well, I wonder how that would run on our system. When Rigetti runs it, they get about 1 solution every 100,000 times. Okay? This is because they don't have what's called error correction. In order to run that problem and get answers every single time, they would need somewhere between 19,000 and 1.9 million qubits would be the best estimate in order to do something called error correction. That's how they would generate 1 solution per run, to go from where they are today, 19 qubits, to 19,000 or maybe 1.9 million, depending on how the error correction really works out in the real world. On our system, we put it in our program, we actually programmed 102 copies of the same problem into our system, and we get answers every time we run it, which means roughly we're 10 million times better than the state-of-the-art gate model system today. This is Google's perspective on what it takes to get a useful gate model quantum computer. This is from their website. They said to get to a useful gate model computer, we need 4 million qubits, and we need the error rates in those qubits to be 100 times less than they are today. So they need 100 times improvement in error rates and 4 million qubits to perform error correction. This is going to take a long time. Even if they grow at twice the rate of Moore's law, the gate model community is going to be 10 to 15 to 20 years before they can really solve commercial problems. So let me introduce you to D-Wave as a company. We were started here in Vancouver. A couple of physicists at UBC started the company. We're headquartered out in Burnaby. We have about 180 people. And one very interesting thing to me here is that our customers have bet $70 million on using these systems already. We have $70 million of real sales contracts for customers to experiment with these systems because they expect that we will take that next step and outperform all the classical computers. How did D-Wave get so far ahead? When these two physicists started the company back in 1999, they spent 5 years just studying the technology and with totally agnostic about which approach they would take. The entire quantum computing industry followed the academic path. The academic path was, let's build a computer that looks like a classical computer with logic gates, sequential logic gates, but make each logic gate quantum. And then we'll see if we can build that device. It turns out it's really hard to do that. In order to do that, you have to create an excited quantum state, essentially a high energy state, keep those particles in the excited state long enough to perform all of the logic gates. And that's very hard. We're talking about nanoseconds for that excited state. D-Wave took this other approach called quantum annealing, which is an analog calculation that takes place in the chip I'm showing you here. It's a superconducting chip the size of your fingernail, and we program that chip to perform all of the calculations in the low energy state. That's essentially why we've made so much progress. It's an easier problem. It's a more natural way to program a quantum device to solve all problems. Let me give you an analogy. It's easier to understand analogies than some of the math. Imagine my problem can be characterized as a minimization problem. And the key is all problems can be characterized this way. Any problem can be cast in this form. And it could have, instead of a 3-dimensional landscape, it could be a 10,000 dimensional landscape, but let's focus on 3. A classical computer is like one person running fast, really fast, up and down, finding the low valley and not quite knowing where to stop, but that person eventually can only run at the speed of light and no faster. Imagine another completely different computing paradigm where instead of looking for that sequential solution, we have like 1 trillion little drones the size of maybe ping pong balls. We throw them in the landscape. They instantly communicate with each other. In fact, faster than the speed of light, they communicate with each other. One finds the lowest valley and they all stop. And that all happens in maybe a few microseconds. That's a completely different computing paradigm that we have now learned how to control and get answers out of. In order to do that, we have had to become the world leader in a number of technologies: superconducting processor design and manufacturing, all of the infrastructure that goes around the device, so refrigeration, input, output, magnetic shielding, anti-vibration shielding. This is the purest, where that chip sits at the bottom, is the purest environment we know of in the universe. Zero magnetism, complete vacuum, and 10 millikelvin, 10 thousandths of a degree above absolute zero. So the technology that goes with this is quite extensive. Within the quantum computing industry, D-Wave leads the patents by far. This is the blue bars are patents, the orange bars are citations. It goes D-Wave, IBM, Microsoft, Northrop Grumman, and then it just goes down from there. In fact, our patent portfolio is so valuable, even though we only have about 165 patents, IEEE Spectrum said it's among the top 10 most valuable patent portfolios in the entire computer systems business. So if you start with IBM, HP, Hitachi, Fujitsu, whoever, we're always in the top 10, as high as 4th in terms of the value of the patent portfolio. Now, where are we relative to classical computers? On real problems, we're about to hit this crossover. Quantum computers scale with what I call double exponential growth. In order to double the power of a quantum computer, I add 1 qubit. It's shocking, so I'll say it again. To double the power of a quantum computer, I add 1 qubit. And so that's why the quantum growth curve is like double exponential growth. And so that's why quantum computers have such potential. We've already shown on benchmark problems These are somewhat synthetic problems designed to test performance that we can outperform the best classical computers with the best algorithms in the world, with the best experts running them. No one can beat us on those problems. On the customer problems that I showed you earlier, we're now just getting to the point where we're starting to break even. So we have, of those 80 applications, there are roughly 24 or so that have statements like the ones you see here. For this problem, D-Wave is about as good, sometimes better, maybe sometimes not quite as good as the best classical systems we can come up with, or the best commercially available systems we can come up with. And we're starting to see more and more examples like that. So, how do we put ourselves squarely in that upper right-hand quadrant on real commercial problems? The plan is, in a way, very simple. Build more powerful systems, make them easier to use. More powerful systems is kind of obvious. We add qubits, roughly every 2 years we double. We add a lot of other features in the chip. For example, we've already built a new prototype with a completely different architecture for the next generation that connects the qubits more densely. Maybe not quite so obvious is the software part. What we're trying to do there is build the software stack from the bottom up. This is sort of a cartoon, but if you're a physicist, you're programming using that equation at the bottom. What we want is a complete stack of software so that your 7th grader can run applications, and that's what we're building. And as we do that, more smart people get on the system and come up with creative ways to use it, and we'll get more and more solutions. The software ecosystem has been built largely so far by our customers, us working with our customers and sponsoring other companies like the Creative Destruction Lab. We found several companies through a program that we sponsored at the Creative Destruction Lab. These are some of our customers. The customers that actually have their own systems installed are on the left. On the right is just a sample of about 24 companies that now access the system over the cloud already to run their applications. We see this being deployed through the cloud in hybrid systems. We won't replace classical computers. We will complement them the same way GPUs complemented CPUs. We'll deploy it through the cloud, and then we'll deliver solutions that will be a combination of cheaper, faster, better, and solving problems that you just can't solve. Now, speaking of the cloud, watch out for this announcement, because if you like quantum computers, starting in October, you'll be able to sign up just like you're buying a pair of blue jeans on Amazon and use our quantum computer. A web platform is coming in October that will allow you to do this with easy demos, instructional videos, libraries of programming tools. The whole point is to get thousands, maybe even millions of developers using this system. We've made a lot of progress in all parts of our business lately. This new generation processor has already been fabricated at a prototype level. We're raising money with companies like PSP Investments. We're announcing new customers in Japan. The executive team has done this before. We have people from Goldman Sachs, former CEO of Cray Computer, the guy who developed the JavaSoft ecosystem, Alan Baratz, is developing our ecosystem. It's a team that's been there. Great investors, DFJ, Goldman Sachs, on. And back to the problems. We're just about there in terms of solving these problems that we talked about. Thank you very much, and I'm afraid not much time for questions.